Hello, this lecture will cover pages 97 through 101 of my lecture notes. So please print those pages out and have them in front of you as I present this lecture on Additional Analysis Techniques, Chapter 5A, Linearity and Source Conversions. Starting out on page 98 of your lecture notes, Additional Analysis Techniques. As a quick review here, we have some quick transformations here I want you to be able to look through and review. Basically, two resistors in series. The equivalent is the addition of the two. Two resistors in parallel. The equivalency is the product over the sum of those two resistors. If you have two voltage sources that are in series with one another, and they're opposing as they are here, the equivalent voltage source is the algebraic sum of the two. In this case, it's V1 minus V2. If these were both aiding one another, plus to minus, obviously the equivalent would be V1 plus V2. And then current sources in parallel. Current sources in parallel add algebraically. You can see these are opposing, so the equivalency would be I1 minus I2. If they were aiding one another, it would be I1 plus I2. If you take a look up here, basically all you're doing to get this equivalent voltage here is you're writing Kirchhoff's voltage law around this loop. And here all you're doing to get the algebraic sum of these is doing a Kirchhoff's current law at this node. Very simple review. On page number 98, I'm going to talk about source conversions. And we're going to be using this a lot later on in the chapter, but I want to introduce it here. A model of a voltage source would look like this. We've talked about this before, where this is the EMF, the source voltage, E sub S. And this internal resistance, this series resistance, is the internal output resistance of this source as you look in from the load. What they usually do is they take that source resistance out and they put it up here. They show it outside of this source, and this source is ideal then in that case. So this is a simple model of a voltage source. It has a source of EMF and an internal resistance which is brought out. The model of a current source shows a source current, and they pull out the output resistance of this practical source and they put it in parallel. That makes that an ideal current source, I sub S, with the internal resistance being in parallel, and then you have the load resistor. This is a model of a voltage source, and here is a model of a current source. If you look between the two of these, you can convert from one to the other. If you have the ideal voltage source, as shown up above here, if you need to get the current, it's simply the short circuit current from this point to this point with the load removed. In other words, you just short these points and you calculate what that current would be. Obviously, it's E sub S over R internal. And E sub S, if you have a source like this and you want to convert back to here, is simply the open circuit voltage that's generated with the load removed. That I sub S just flows through R internal, because this is an open circuit out here, and it generates a voltage here, which is I sub S times R internal, which is E sub S. So you should be able to go back and forth between these two sources. An example down here. Let's say you have a voltage source, and the voltage source has 10 volts with a series 2 ohm resistor, and it's connected to a load resistance. If you want to convert this to a current source, you basically short this out and you calculate what that current would be. You can see it's 10 volts divided by 2 ohms, which is 5 amps. And then you bring this series resistor down in parallel, and then you can attach R back onto the circuit. These circuits although they're not identical, they look exactly the same to that load resistor. That load resistor, independent of the value of that load resistor, it sees no difference if it looks back in on this circuit or it looks back in on that circuit, because these two circuits are equivalent. Let's go from here back to this point. If you're given this current source, you want to get back to a voltage source, you remove the resistance, you calculate that open circuit voltage. Well, you have the 5 amps flowing through the 2 ohms, it generates 10 volts. Then you bring the resistor from parallel up to series. So you'll be able to go back and forth between these two sources. What I'd like you to do is stop the video, look on page 99, and I want you to get the equivalent voltage source for this current source and draw it over here. Get the equivalent voltage source for this current source and draw it over here. Get the equivalent current source for this voltage source and draw it over here. And get the equivalent current source for this voltage source and draw it over here. You should be able to do these in your head. I made the calculations simple. You don't need a calculator for it. So try these 4 source conversions and see if you get the same answers I do. If you did that correctly, here are the answers. That's what I would expect for the 4 answers in this on this page. Make sure you know how to do that. On page number 100, the last thing, one of the things I want to mention here is through the remainder of this chapter, we're going to discuss 5 more analytical techniques. They're going to include linearity, which we'll finish up this lecture with. We have a lecture on superposition. We have a lecture on Thevenin's theorem. We have a lecture on Norton's theorem. And then we have a lecture on maximum power transfer. You're going to be using these the rest of this course. And you'll be using all of these in other courses. Let's start out with linearity. How can you use linearity as an analysis technique in solving parameters within a circuit? In the first lecture, we showed that the resistor was a linear element because its current voltage relationship was linear. That's Ohm's law. V is equal to I times R. Or in the form Y equal mx plus B, V is equal to R times I plus B, where B is the intercept, the y-intercept, and R is simply the slope. That's a linear relationship. There's a linear relationship between voltage and current in a resistive circuit, where and the relationship between the two is the constant R. That's the slope. On page number 101, or in terms of the time domain, the voltage with respect to time is equal to the current, is equal to the resistance times the current with respect to time. Linearity requires both additivity and scaling to be able to go through the analysis I'm going to show you in a minute. Additivity basically says if the voltage 1 with respect to time is equal to R times I1 a t, and voltage 2 with respect to time is equal to R times I2 a t, then the addition of V1 a t plus V2 a t is simply equal to the resistance value times the algebraic sum of those two currents. If this looks simple, it's because it is. Linear equations are fairly simple. Scaling. What's scaling all about? Well, in order to do this analysis I'm going to show you in a minute, the linearity requires scaling as well. If V1 at t is equal to R times I1 at t, that's simply Ohm's law in the time domain, then some constant times V1 at t has to be equal to R times the same constant times I1 of t. So how does this linearity help us analyze circuits? Well, the best way to show this is through an example. And they have an example in the book 5.1 that looks like this. Here's a simple circuit, resistive circuit, and they want you to find V out. Well, we've done this in previous chapters. I mean, basically, to find V out, you have to find the total resistance, which puts this plus this in series, in this plus this in parallel with this, and that equivalent combination in series with this. Get a total resistance, divide it by 12 volts, and get this I sub O current, which we called the total current. And then work with current divider rule outwards to find out what that voltage is. But there's another way. We could use linearity. And you should be able to do this in your head. That's how this problem was intended, to be able to just illustrate linearity in your head. We're going to assume, we don't know what this output voltage is without going through an analysis like I previously discussed, but we're going to assume it's 1 volt. Let's assume you have 1 volt out here. And we're going to work backwards and see what that results here in this new VO value, this new value at this point, voltage here. And then we're going to use a proportion to find out what this really is. So we're going to assume V out's 1 volt here. If there's 1 volt at this point, the current I2, which I labeled, has to be equal to 0.5 milliamps. You have 1 volt divided by 2 k ohms. It's 0.5 milliamps flowing here. V1 at this point then has to be equal to this resistance here times that 0.5 milliamps times the voltage drop across this 2 k ohm resistor, which is also 0.5 milliamps times 2k. This current and this current are the same currents because this is an open circuit. So if you look down here at V1 at this point is simply going to be equal to the voltage drop here plus to minus, the voltage drop here plus to minus, so they just add 4k times the I2, which we already know, that's 2 volts, plus 1 volt. How do we get 1 volt here? Well, the 1 volt here is simply going to be equal to what we assumed when we started out. You get 3 volts at this point. I1, let's calculate I1. Well, if you know this is 3 volts at this point with respect to ground, this is all referenced with respect to ground here. I1 is simply equal to V1 divided by 3K. That's 1 milliamp. If you have 1 milliamp flowing here, and you have a half a milliamp flowing here, that gives you 1.5 milliamps I0. Taking our time and just doing this step at a time. If you have 1.5 milliamps flowing here, plus to minus, that gives you, we're going to calculate V out now, the voltage here. Assuming you had 1 volt out here. Well, it's equal to 2K times that I0. That's the voltage drop here. We know I0. We know the 2K. 1.5 milliamps times the 2K is 3 volts plus V out, V1. That's just Kirchhoff's voltage law around this loop here. V out is equal to 2K I0 plus V1. That's 6 volts. So what we've done is we assumed 1 volt out here, and it gave us 6 volts back here. So I say as a simple proportion now, 1 volt out on the output yielded a 6 volt back here. That has to be proportionate because of linearity. The unknown value of V out is to the actual 12 volts. V out is 2 volts. We calculated V out of this circuit using linearity by first assuming 1 volt here and working backwards to get this V out parameter. And then we said that 1 volt was to the 6 volts that we calculated, as X is, our unknown, V out is to 12 volts. what I'd like you to do is look at the learning assessment E51, and it's in your book right here. I'm not going to work this out because I think you can do that. I want you to look at this problem right here. And they say in this problem, use linearity and the assumption that I0 is 1 milliamp to compute the correct current I0 in that circuit. So here you have I0 out here. Okay. And you want to calculate what I is. Well, you can use your analysis techniques by getting an equivalent resistance over here and getting this equivalent resistance and use a current divider rule and work outwards to find out what I0 is. But what we're going to do is we're going to assume that I0 is 1 milliamp. I want you to assume that I0 here is 1 milliamp. And I want you to work backwards. And that's what I did here with my chicken scratch in here. And I calculated I as 6 amps. Or 6 milliamps, I'm sorry, it's 6 milliamps. So I said the 1 milliamp I assumed is to 2 milliamps as X is to 6 milliamp. And I calculate X, in this case I calculate I, to be equal to 3 milliamps. That's linearity. I'm not going to probably test you on linearity, but I want you to know its usefulness. And that concludes the lecture.